So today I'm going to present the work for my thesis, which is titled Systematic Conservation Planning in Marine Environments, looking at the sensitivities of the planning process to aspects of scale. So as you can imagine, much of this talk revolves around this concept of scale, which is a fundamental conceptual problem across arguably all fields of science, as you're probably aware. And likely as a result of this, it's actually used ambiguously to refer to different concepts, but related concepts, such as extent, refers specifically to the spatial size or the area, and resolution or grain, which refers specifically to the precision that's used in measuring something. So the most obvious example is like the number of pixels you would have in a screen. And so when I refer to scale in this talk, specifically I'm referring to the definition you see up there, which is the spatial, quantitative, or analytical spectra that are used to measure and understand social-ecological phenomena and the relational comparisons between different points along these spectra. And so when I refer to this word level, I'm referring explicitly to the units of analysis that are located upon the different positions of these scales. So at the bottom, I just have some examples there: spatial, temporal, and jurisdictional scales, and on them are the different levels of analysis that you might measure any of these scales. And so I'm looking at this concept of scale within the context of systematic conservation planning, which is the process of allocating conservation interventions in space and time. While that sounds pretty straightforward, in reality it's not actually, because we need to understand what's the best thing to conserve, or where should we put these actions where we conserve things, or how should we do it, how should we distribute it in time. And on top of that, all of this changes when you change the reason why you're doing these things. And so all the while we have to do this with very constrained resources. And so what we see is at the moment there are millions of dollars being spent on planning initiatives every year, but we're not actually seeing them being translated into effective actions on the ground. And so understanding how to plan and implement conservation effectively is actually really important. And so this is just a structural framework for how systematic conservation planning works. There's 11 main stages, and you need to read and understand every single stage. The only point that I want to make here is that nearly half of these stages involve decisions that are directly related to scale. So these can be described into two broad groups. So first of which is more technical concerns, so what resolution you collect your socioeconomic or biodiversity data, and the other half are address more practical concerns of scale. So what's the best scale to plan at? How do we transition from a regional scale planning to a local scale of implementing actual actions? So this brings me to the overview of my thesis, which is to understand the influences of scale within the systematic conservation planning framework, with the ultimate aim of improving this framework to deal with scale more explicitly. So this is just how my chapters are situated. The first chapter looks at these technical concerns. My second chapter focuses on transitioning from those to those of more practical in nature, and the last two chapters focus on the more practical concerns. And because they're quite conceptually different, I'm going to go through the introductions and the gaps each one at a time, rather than just overload the other side. So the first chapter, technical concerns, are a big fundamental part of systematic conservation planning is this process where we systematically identify priorities across the region. So I'll just step through that process with you now. We call it spatial prioritization, and it involves taking your area of interest. This is an example data set of coral reefs off Fiji, and then we would subdivide the region into planning units so that we can feed that information into a software that runs on an algorithm that prioritizes the most efficient reserve solution. So you would give it a problem, which is, let's say we wanted to conserve 20% of each habitat type, and then it would spit out what would be the most optimal solution. And so in this process, there are three main modes of resolution at play. The first of which is the spatial resolution of the data that you use. So either the habitat data or socioeconomic data, which is often used in this process to determine the most cost-effective solution. The second is the thematic resolution at which you have your data. So that basically speaks about how detailed the categories are. So in this case of this coral reef habitat, a low thematic resolution would just be 3 reef classes, for example, while a high level might show you 20 different types of reef classes. And lastly is the spatial resolution, or the relative size of the planning units that you use. So these can be really big or really small. And so what we do understand now pretty well is that these characteristics do influence how spatial priorities are determined. But most of these studies have looked at these factors individually, even though in any one prioritization, all factors are equally relevant and are occurring at the same time. And they've also only really looked at this for terrestrial environments. So related to this is the fact that recently, you can see examples here, in those maps there have been lots of global and regional assessments done on priorities. And the problem with that is that there's a correlation that we see between the very large planning extents and the resolution of the data that's used. So they tend to be very coarse resolution. And as well, the planning unit sizes that they can feasibly use to put into the software. So they also tend to be really large. And the problem with that is that it's not at a fine enough resolution for the level that we actually would apply actions at. And so what's often suggested as a solution to overcome that is to use these really broad assessments to guide finer resolution assessments. So with the example at the bottom here of the coral triangle, we would take those big squares, identify coarse priorities, and then get data at finer resolutions within those, and then rerun those prioritizations. But the problem with that is that it makes this assumption of nestedness, which is that if we were going to do that, you are implicitly assuming that within those coarse priorities are where you would find your fine resolution priorities, and you would miss out if there were any lying outside of those coarse priorities. So this leads me to my first research gap, which is understanding how these technical aspects of setting spatial priorities influences where they're determined in space, and how this relates to the ability of coarse resolution priorities to represent fine resolution priorities. So the research questions for this chapter was, how does planning unit size, thematic resolution of habitat data, and the spatial variability of socioeconomic costs interact to influence these spatial priorities? And secondly, to what extent do these coarse resolution priorities represent fine ones? So I took Fiji and Micronesia as my case study regions, and I used the prioritization software MarkSan because it's the most widely used across the world. And I ran all of my prioritization scenarios with this blanket conservation objective to reserve 30% of all habitat features. So this was the study design that I used. I looked at 2 planning unit sizes, large and small, and 5 levels of thematic resolution for the habitat data. So 1 being the lowest, there was 11 reef classes, and 5 being the highest, which had 280 reef classes. And then I looked at 2 different types of socioeconomic cost data. So the difference being that 1 was spatially uniform, in other words, across the entire region, costs were the same, and the other one spatially variable, which was calculated on a proxy for cost to fishes. So the closer you were to fishes, the more expensive it was to reserve that planning unit. So in combination, that gave me a total of 20 prioritization scenarios, which were run to produce 100 unique solutions. And one thing I want to point out is that in a MarkSan run, it gives 2 main outputs, the first of which is the optimal or best solution, and the second is some measure of how irreplaceable each of those planning units are in terms of your objective that you're trying to achieve. And so with that best solution, that information is basically a binary data set, 0 for planning units that are not selected and 1 for planning units that are selected. And the good thing about that is that it's analogous to presence-absence ecological data. So that allowed me to do some neat spatial similarity statistics on each of the solutions that were produced. And so what did I find? When looking at how spatially similar each of the identified priorities were between the 20 scenarios, this is what I got. And so that's a pairwise comparison of the individual 2,000 solutions that were generated. The red shades represent the scenarios with large planning units and uniform costs, with each of the different 5 shades representing the level of thematic resolution. And so the same with the green, large planning unit, variable cost, blue, small planning unit, uniform costs, and the purples are small planning unit with variable costs. And the main thing that I just want to point out is this difference between how the solutions spatially differentiated depending on whether the priorities were identified with uniform cost versus variable cost. So where there were variable costs is you can see a distinct clustering between each of the levels of thematic resolution. So there was an interaction effect here between the spatial variability of the cost layer used and the different levels of thematic resolution. And so with the second question of trying to understand how the ability of these coarse priorities were able to represent the fine resolution priorities, on the left on the map here is coarse priorities identified with uniform cost. And what you can see, so the people represent where they live, and you can see that the priorities are identified pretty uniformly across the region, whereas on the right here, which is coarse priorities identified with variable cost, you can see how the priorities identified are spatially biased to be further away from people. And so what I found actually, so this smaller map at the top here is an example of those fine resolution priorities. And as it turns out, the uniform cost coarse priorities did a better job of incidentally representing those fine resolution priorities than the variable cost ones, which were spatially biased to be far away. So in summary for this chapter, I found that the spatial variability of that socioeconomic cost data had the strongest influence on where priorities would be determined. And this is likely a strong result of the fact that the algorithm that's used is designed to always look for the most cost-effective solution, so it will tend to find the most cheapest planning units where possible. There was an interaction effect between the thematic resolution and the cost variability, and coarse priorities identified with uniform costs better represented these fine priorities. So some recommendations from this chapter were, where possible, use smaller planning units and finer resolution data, which is pretty obvious and not always going to be possible. So in those instances, it's better to use a uniform cost layer at that broad scale if you're going to want to narrow down to finer resolutions assessments after that. And that has implications in the field of conservation planning, because lately, not too long ago, was this big push to incorporate socioeconomic costs at all costs, and so they were doing so at really coarse resolutions at regional levels, and so that actually has implications for if you want to drill down to more finer scale. So moving on to my chapter 2, where I start to look at this transition from these assessments to actually implementing actions. And so what we see here is this really strong mismatch of scales, right? We're planning at a regional scale, but we actually implement actions on the ground at these local fine scales. And so part of the problem that we have with doing this is all the changes that are necessary when we move between these different scales. So for lots of reasons, changes come up, such as constraints or new data or negotiations that you actually have to do with people who are in charge of the resources on the ground. And so a solution that's been suggested in the literature is to overcome this mismatch is to have multiple iterations between these two scales of perspective. So to go from a regional scale, and as you implement at the local, you would feed that information back to the regional scale to update what you know and so on, to account for the changes that need to happen as you shift between the two scales. But there is a really big research gap here, and that's that we have poor understanding on how to operationalize this, what I'm going to call from here on, iterative planning, and the implications of doing this in practice. So the research question for this second chapter was, how does the frequency of updating these regional priorities influence the total time taken to achieve your objectives, the total extent of what you finally implement, and the spatial overlap between what you initially prioritize and what you finally implement on the ground? So I looked at this research question using Fiji as a case study. So if you imagine this hypothetical planning context where the national government of Fiji has identified priorities at that national scale, which is shown in the map, those circles, they would then use this information to direct resources to send planning teams to these identified provinces and then send teams to go and negotiate with people on the ground and find out what's actually happening. Finally, implementing marine reserves, which of course would not match up perfectly to the priorities that were identified at the national scale to begin with. So then ideally you would feed that information back, update your priorities, rerun your prioritization, and so on and so forth until you've achieved all of your objectives. And so while this, at the start of this chapter, it was not possible to simulate this process with Marxan, we made it possible using the great coding language of R that we all know and love. And so I ran all of my scenarios again to have this blanket objective to save 30% of all habitat features. And for this chapter, I had 4 simulation scenarios, which basically altered the update frequency. And the way that I did that simply was to change the number of planning units that would be implemented as marine protected areas before we rerun a regional scale prioritization. So that changed from every 25, 50, 75, 100 planning units. And from here on, I'm just going to short form those scenario names to scenario 25, scenario 50, scenario 75, so on, with scenario 25 being the most frequent updates. And so what did I find? For the total time taken to achieve all conservation objectives, here is the result. On the x-axis is the time elapsed. On the y-axis is the amount of feature reserved expressed as a percentage. So the black dashed line is our 30% objective. And the 4 scenarios, so scenario 25 being the most frequent updates, and scenario 100 being the slowest updates. And surprisingly, there wasn't actually a significant difference between the time taken to achieve all of our objectives between the scenarios. But where there was a difference was how quickly they were able to achieve objectives for rare features. So each of the lines represents one feature, the red being more rare and the blue being more common. And you can see in the graph with the frequent updates that those red lines hit that 30% objective a lot sooner than the scenario 100. So while I didn't find a difference in the total time taken, where I did find a difference was in the number of unique planning units that were investigated. So on the x-axis, again, are the scenarios, 25 being the most frequent updates, 100 being the least frequent updates. On the y-axis is just the unique number of planning units investigated. So what I found was that when priorities were being updated more frequently, the simulations would go back to the same planning units to implement more actions within compared to those that were updated less frequently. And so for the total extent of the final implemented reserves, again, I didn't find any significant difference, which at first was counterintuitive, because if you imagine a boat rudder that's trying to, get the boat along a path and it has to account for currents, the more often you account for those deviations from your true line, the more efficient you think your path would be, but it didn't seem to be the case. And for the spatial overlap between initial priorities and final reserves, this was a bit more intuitive in that the overlap was greater when you were updating your priorities less frequently. So that makes sense, because if you're taking greater chunks of your priorities and implementing them before you update, more likely you're going to get a reserve system that's more similar to your original plan. So in summary, for this chapter, I found that update frequency did not actually influence the total time taken or the final extent of reserve systems, and that probably has a bit to do with the fact that these simulations were designed to have a constant implementation rate. So if the time doesn't change, then the extent's not going to change either. Update frequency did, however, influence the potential to reinvestigate planning units and how quickly rare objectives were achieved. And the spatial overlap between initial priorities and final reserves was greatest when you had the fewest updates. So just the main recommendations from this chapter were these two potential benefits that I identified to updating your priorities more frequently. So if you happen to be in a planning situation where you have a lot of rare features that are at risk, then it might be useful to update your priorities more regularly. As well, if you are in a planning context where it costs a lot of money and resources to get onto the ground to negotiate with communities and establish those relationships and trust, then you might actually be more cost effective by regularly updating your priorities and capitalizing on this potential to go back to previous areas. That brings me to chapter 3, which is where I start to look more at the practical concerns of scale within this process. And to begin with, asking, is there a best scale to plan at to begin with? So it's widely acknowledged in the conservation planning literature that, we do need to consider all of these different scales that we understand are going on socially, ecologically. But the thing is, we still don't understand the best approach to do so or how it's being done. So this leads me to fill this or address this third research gap, which is to first understand how conservation plans developed at these different levels are able to address the different social and ecological scales, with the rationale that once we understand that, we might be able to integrate across them a bit better. So the third research question that I address for my third chapter is, what are the relative strengths and weaknesses of conservation plans developed at different scales in addressing these different parts of a social-ecological system? So I took the coral triangle as my study area, and I used this adapted socio-ecological systems framework from Graham and colleagues, which, as you can see, just splits it up into the different scales, in this case, the jurisdictional levels at which we would plan at. So from the international, regional, down to local and patch, and then the different patterns and processes that occur at these different ecological and social scales. And so I reviewed all of the peer review and grey literature to find all the conservation plans that I could that were developed at these different levels, so from international right down to the patch level. And then I extracted all of the ecological and socio-economic objectives that were stated in each of these plans. And once I got those, I then took that framework and identified which part of the framework each objective addressed, and then the adequacy with which they were able to address those. And that was done using these two classification schemes, one for ecological, one for socioeconomic. And basically, without going into too much detail, they just go obviously from good in green to not so good in red. So for ecological, the good was going from quantitative and justified ecologically objectives down to qualitative, so those that were just more descriptive in nature. And for the socioeconomic objectives, I look at this in the context of stakeholder engagement. So that went from having decision-making power as good down to information where they were basically just told what was going on. And so I'll just run through an example of what I found for one plan as I evaluated all of these plans. So this is an example of Ninoconis from Timor-Leste. That was a local protected area, so that's highlighted here in that framework. And it addressed ecological objectives at that same local level to a reasonable extent, so that yellow, which means it was all right. And patch level ecological objectives to a less greater extent, identified or represented with the red. And then similarly for the social objectives, it addressed social objectives at that local level great, and at lower levels not so great. And so I did this for all of the 18 conservation plans that I found, and I called this fingerprint of scale performance. You can think of it the term scalar coverage. So I'll refer to it with that from now on. So I'll just show you what I found for the ecological objectives overall. Each wedge of this pie represents the conservation plan that I evaluated, so there's 18 in total. The inner circles represent objectives that targeted the patch level, all the way out to the outer circle, which is objectives at that international level. And the thick black line basically denotes the level at which that plan was developed. So there are 2 patch level plans, 6 local level plans, 8 regional, and 2 international. And the colors are just the adequacy of addressing the ecological objectives. And so the thing that I just want to point out mainly is that, as you can hopefully see, every plan was best able to address ecological objectives at the same level at which that plan was developed, and then less well for every level that was further away from it. So as it got lower, they tend to address them less well. And the other thing to note that I want to point out is just that these high-level plans, so the regional and international level, demonstrated a greater capacity to address these ecological objectives, as you can see with all the greens. And so for the socioeconomic objectives, I found a similar pattern where stakeholders were only engaged at that same level of the plan or lower as well. And the number of groups that were engaged varied greatly between planning levels, but this was greatest in number in local level plans. And the extent of engagement was also highly variable between groups. And what I found was reflected most closely in this pattern was the kind of governance system that was in place where the plan was developed. So in summary, for this chapter, I found that no conservation plans I evaluated had this full scalar coverage, but higher level plans did demonstrate a higher capacity for scalar coverage and most adequately addressed ecological objectives. And the diversity and extent of stakeholder engagement was highly variable across all levels of planning. So some recommendations from this chapter were that conservation planners can actually use this framework to assess their own plans and identify any weaknesses or gaps in addressing these different social and ecological elements across scales. And since there is clear strengths and weaknesses of planning at each level, we actually probably need all levels for the greatest chance of complete scalar coverage. And what's necessary are these vertical interactions between the different planning levels. And because higher level planning demonstrated a higher capacity for scalar coverage, it should fall on them to link to the planning that occurs at lower levels. So this brings me to chapter 4, which is where I look at this idea of multi-scale planning. So at this point in my thesis, it was pretty apparent that we can't just consider one scale, we have to consider multiple scales. And so I looked at how it's currently conceived in conservation planning, which is as scaling down and scaling up. So in the scaling down approach, which is like an offshoot of top-down management, what you see is planning initiatives starting at higher levels and then progressing to lower levels, and as it does each time, incorporating local preferences and objectives. So an example of that might be the Aichi targets in the Convention of Biological Diversity. They've set that at an international level, and then all the countries that are signatories include it into their own national plans. And so scaling up is basically the reverse. What you have is, it's an offshoot of bottom-up management, so you have locally driven initiatives that are all separate, happening at these local scales, and then these are brought together in a broader context at higher levels. So a good example of that is what's been happening in the Philippines, which started that way, and now they're trying to turn them into functional networks at a regional scale. And so both scaling down and scaling up are advocated for in the literature because of their strengths. But it's unclear whether this dichotomy actually exists in practice, and we have a pretty poor understanding on the best way to approach this. So that leads me to my fourth research gap that my thesis addresses, which is understanding if multi-scale conservation planning does occur in practice, and if it does, to what extent, how it occurs, and what are some of the conditions that influence this. So the research questions for this chapter was, does multi-scale planning occur in practice? If so, how do planning processes inform one another at these different levels? And what are some of the factors that can impede or facilitate multi-scale planning? So the explicit definition for multi-scale planning that I used for this chapter was where planning processes undertaken at different scales effectively inform one another and consequently result in improved outcomes compared to processes undertaken at just a single scale or at multiple scales without informing one another. So I used Papua New Guinea and the Solomon Islands as my study regions for this chapter. And then I identified all the planning processes that I could that have occurred at these different jurisdictional levels. So the local, provincial, and national level. And I've just shown you on the left there just the kind of spatial extents that these different jurisdictional levels speak to. And once I identified those, I collected all the reports and planning documents that I could on all of them, and then used that information to map out in space and time, so in this case space being jurisdictional levels, how they sat, to try and get at this understanding of how planning is occurring across these multiple scales. And then I conducted in-depth key informant interviews with the conservation planners that were intimately involved in these processes to gain more understanding and fill in my knowledge gaps here for how planning processes were informing one another, if they were, and how this was associated with outcomes. And so what I found is that multi-scale planning does occur, but rather than this neat idea of scaling up or scaling down, it's far messier. And I found that planning processes inform each other primarily through these three different flows, the first of which is through data or associated conservation objectives. The second is the experience of the planners that were involved. And the last was institutional support, which was often associated with funding. So the thing that I just want to point out is what was apparent was that some levels were characteristically associated with certain types of flows. So for example, the international level was only ever associated with flows of data and institutional support. And so just to bring you back to the second research question for this chapter of what factors can impede or facilitate multi-scale planning, in the interviews that I had with the conservation planners, I thematically analyzed that qualitative data so that I could try and understand these factors. And I did so using this evaluation framework by Madeline and Bob, which evaluates outcomes in the context of these 5 different forms of capital. So natural, financial, human, social, and institutional. And while I found that a lot of these attributes or themes that emerged from my qualitative analysis did fit within these 5 forms of capital, there were a number that were scale explicit and didn't quite fit. And so as a result, I proposed this new form of capital, which I term scalar capital, defined here as the explicit consideration and application of the understanding of these important dimensions of scale as they pertain to multi-scale planning. And so from this qualitative analysis, all of these interviews, those themes that didn't quite fit are here as these dimensions of scalar capital, which are multiscalar understanding, scale jumping, leadership characteristics, stakeholder engagement, policy frameworks, and institutional frameworks. And while the last 4 are familiar concepts in the conservation planning literature and probably familiar concepts to lots of you, as dimensions of scalar capital, what's emphasized here is the need for them to be explicitly present across all levels of planning. And these 2, which are more novel dimensions to the conservation planning literature, these are the ones that I'm going to go through with you today briefly. So the first, multiscalar understanding, speaks to this idea that And that's what emerged from the data, that planning at each level seemed to serve very specific purposes. So this supports what I found from chapter 3, that each level seems to have its role to play. And so the example that I'm showing you here is for national level planning processes. And what emerged was that it served to provide these two main purposes, and that was to fulfill the requirements of international commitments, and this was often associated with accessing large funding schemes, as well as directing limited resources for planning at lower levels. And so it occurred a number of times where planning teams involved in these national level planning processes, if they had expectations outside of this, which was often the actual implementing of actions, they would often be disappointed and have perceptions of wasted effort, because they would never eventuate. They would only serve these two purposes. And so the second dimension of scale jumping, which is defined as the ability of actors or organizations to interact or operate across these multiple scales. I'm going to talk you through one example which emerged from the data, which is outlined here in the schematic, and those pictures are from this example. Local communities were brought together in a planning workshop to map their knowledge of all of the logging that happened in each of their communities that they were aware of. And at the end of this workshop, they put all these maps together. So that's the bottom photo there. And it was the first time that all of these individuals from these communities were able to see the full extent of logging concessions across the whole province, which prior to this workshop, they just didn't have the capacity to do so. And so that's what this little schematic demonstrates. The scale constrained actors in this case are these members of the local communities. The scale jumper is the conservation planner. And through that planning workshop, they elevated their decision-making to a high-level provincial perspective. So in summary, for this chapter, I found that multi-scale planning does occur, but rather than scaling up and scaling down, it's multi-directional scaling. And plans primarily inform each other between levels through data, objectives, plan experience, institutional support, and funding. And I found that scalar capital is an important new form of capital that we should be considering. And when dimensions of scalar capital were present, there was improved outcomes for multi-scale planning. And importantly, this chapter also showed that there is empirical evidence for ways that we can actually foster scalar capital. So the main recommendations from this chapter are that scientists and policymakers should integrate scalar capital into existing evaluation frameworks to improve outcomes across these multiple scales. And where possible, conservation planners involved at any level should foster scalar capital to accrue these flows of planning resources across scales and time. So in conclusion, from my overall thesis, what I found is dealing with scale in conservation planning is a complicated and messy affair. And as a result, conservation planners need to explicitly consider scale throughout that process. And I've shown throughout my thesis the specific ways and points in that planning framework in which we can hopefully do so in the future. And it's most useful to think about this in the context of a multi-scale social-ecological systems framework. Also, that we need to undertake conservation planning at the different levels and consider them as one connected planning system rather as processes that occur in isolation from each other. And lastly, that scalar capital can be fostered, and investing this form of capital into planning processes can lead to improved outcomes across multiple scales. These are some research outputs from during the time of my thesis. So the first my four data chapters, the first two of which have been published. The second two are in prep and hopefully close to submission, and some other reports and papers related to my thesis. And with that, I just want to say a really huge thank you to, of course, my supervisor team. Unfortunately, Bob wasn't able to make it today, as well as Jeremy and James, who used to be my supervisor, but who's left JCU, Tiffany and Graham for your really useful expertise on my last two chapters, and of course all of the people who have data and access to workshops that said yes to me even though they don't know who I was at all. And of course a lot of technical guidance and expertise from the eResearch Center here at uni, as well as the key informants, workshop organizers and participants, Bob's lab group for all of their conservation planning wisdom, friends and family, and as well as all the admin staff from the college and the center and JCU for the amazing postgraduate research scholarship that I've been given.